This is the fifth unit of the dynamical systems primer on invariant manifolds, which is about the behavior of the dynamics near a fixed point. So behavior near a fixed point. Near a fixed point, let's call it P, right? So that means that f of P is equal to 0. And we have the linearization at P, and we can presume that we understand the dynamics of the linearization because we can get it from the spectrum of df of P, which is an n by n matrix. And we want to conclude from that the behavior of the full nonlinear system near the fixed point. And basically, the story of invariant manifolds is that the structure of the linear system, right, this is the linearized system, goes through locally to the full nonlinear system, to the full nonlinear system. In other words, this sort of behavior here, right, of E minus, E0, and E plus goes through into the behavior near the fixed point P here, right, in some neighborhood of the fixed point P, in kind of a sort of curved version of each of these subspaces, and that's what the invariant manifolds are. So near this point P, there will be a manifold, if you will, a sort of curved version of E minus going through P, which we call the stable manifold, a curved version of E plus, and a curved version of E0. E plus, the curved version, is called the unstable manifold, and E0, the curved version, is called the center manifold. So the E minus corresponding to that is what we call WS loc, the stable local manifold. Stable local manifold. And corresponding to E plus is WU loc, which is the unstable local manifold. And then corresponding to E0 is WC loc, or the local center manifold. And the picture you could think of as follows. And so E minus, those go in, E plus, those go out. E0 is the center stuff, so I'll depict that as kind of a curve of fixed points. And then corresponding to this, but inside the neighborhood P here, right, this is P, is WS loc, that's the curved version of E minus, WU loc, the curved version of E plus, and then WC loc. On WS loc, the dynamics are converging towards P. WU loc, they're converging towards P in backward time, and WC loc is kind of the stuff that isn't doing that isn't decaying exponentially. But remember that this picture is only sort of local, right? So this is kind of in this neighborhood of P, if you will, right? So this is in this sort of ball based at P. So these manifolds are invariant. So we've got WS loc, WC loc, and WU loc, corresponding to stable, center, and unstable. And they are invariant under the flow, relative to a neighborhood of P, In other words, you prescribe some neighborhood of P, and if you start on one of these manifolds, you stay on them unless you leave the neighborhood. So that's what invariant relative means, and that's why they're called invariant manifolds. Manifolds because they're sort of curved versions of the subspaces, and invariant for this reason here. So what does it mean to say that they are based on the subspaces? Well, they are actually graphs, right, from their respective subspaces, right, to a complementary subspace, right, of Rn. So in other words, Ws loc is like its domain, it's the graph of a function, and its domain is E minus when shifted to P. Wc loc is E0 when shifted to P. Wu loc is based on E plus when shifted to P. And also, importantly, each is tangent to their own subspace. Okay, so Ws loc is tangent to E minus, and etc. Okay, just to reiterate, Ws loc consists of trajectories decaying to P exponentially. Wu loc decaying to P exponentially as t goes to plus infinity. This consists of trajectories decaying to P exponentially as t goes to minus infinity. And Wc loc contains trajectories that do neither. So they do not decay exponentially in either forward time or backward time, just like in the linear case. But lots of different things could happen on the center manifold. So here's a key sort of fact, which is that Ws loc and Wu loc are determined by the exponential decay condition, are determined uniquely by the exponential decay condition. Right? Wc loc is not unique. It's very easy to come up with examples of a number of different center manifolds. In one particular, just the same situation, the same equations, the same fixed point, and so on, where there are a number of different manifolds that you would happily call a center manifold. Use the term loc here, putting that as a sort of subscript on these things, because these are local manifolds, but you can easily form global manifolds, although technically actually they're not manifolds, but that gets to be kind of involved, but we sort of call them that. So you can form the global stable manifold by taking the union of the local, any particular local stable manifold dotted with T, where you go backwards in time. So you take the union over all backward iterates of Ws loc. So this is the global stable manifold. Right? And then similarly you can do the global unstable manifold, which is the union T bigger than or equal to 0 of Wu loc dot T. It's the global unstable manifold. It honestly doesn't really make sense to talk about the global center manifold. That is really just a local object. Okay, so this completes the unit on invariant manifolds.